In this video tutorial, we will learn to draw simple hydrocarbons such as alkanes, alkenes, and alkynes. The simplest type of organic molecule is the hydrocarbon. It's called a hydrocarbon because it primarily consists of hydrogen and carbon atoms. In general, there are three basic types of hydrocarbons, and they are the alkane, the alkene, and the alkyne. Common examples of alkanes that you will encounter in your everyday life include methane, propane, butane, and octane. You may notice that every single one of these compounds ends with the suffix ane, and that's just there to show the reader that they belong to the alkane category of hydrocarbons. If they had been alkenes, then they would have had an ene suffix, and if they had been alkynes, then there would be a yne suffix. In general, alkanes are simple hydrocarbons that are bonded exclusively by single bonds. As such, their carbon atoms are said to be saturated, so they are bonded with the maximum number of hydrogen atoms possible. Alkenes, on the other hand, contain at least one carbon-carbon double bond, while alkynes contain at least one carbon-carbon triple bond. Now, the general formula for alkanes is CnH2n plus 2. Now, in this example, I have 3 carbon atoms, so my N value is 3. And the number of hydrogens I have is 2n plus 2. Since n is equal to 3, then 2 times 3 is equal to 6, plus 2 means I have 8 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. So if I had an alkane with 72 carbons and I wanted to know how many hydrogens were present inside this molecule, instead of drawing a 72 carbon chain and counting every single individual hydrogen in my diagram, I can just plug it into the generic equation, 2n plus 2, where n equals to 72 in this case, giving me an alkane chemical formula of C72H146. Now, if this were an alkene, the general formula would be CnH2n. You'll notice the plus 2 has disappeared. By placing a double bond in the chemical structure, my carbons now have too many bonds. They're only allowed to have 4 bonds, but in this case, these 2 carbons have 5. To make room for this, I need to remove these 2 hydrogens, and now our carbons satisfy the octet rule. But in so doing, I've lost the 2 hydrogens over here. The same goes for alkynes. By inserting a triple bond, I again have 2 carbons with too many bonds associated with them. So in order to fulfill the octet rule, I need to get rid of these 2 hydrogens, which is why the general formula has a minus 2 for the hydrogens now. So each time you go from a single to a double to a triple bond, you have to remove 2 hydrogens in order to make room for it so it does not violate the octet rule. Now, if you'll recall from previous lessons, function follows form, which means that the structure of an organic molecule has a significant impact upon its physical and chemical properties. Due to isomerism, whereby the same chemical formula can result in different chemical structures, a more detailed naming system is required to explicitly or specifically tell the reader which version, which isomer, which structure are we referring to. So let's take a look at this example over here and chunk it into smaller pieces to see what each part represents. One way to look at organic nomenclature is to think of it as a tree. And if you look all the way at the end of the name, you'll see information regarding the parent chain. This is like the trunk or the root of the tree, from which all the other components sprout or branch off. And looking at this component, we see there's 2 pieces of information. We see the ane suffix that tells us it's an alkane, so only single bonds are present in this chemical compound. And we also see the hex prefix, and that tells us the number of carbon atoms in the parent chain. Now, these prefixes should be familiar to you, as you would have learned them in previous courses. The only big difference being the first 4 prefixes, instead of mono, di, tri, tetra, they're now meth, eth, prop, bute. So methane has 1 carbon in its parent chain, propane has 3, while butane has 4. Some students use the phrase, monkeys eat peeled bananas, so monkeys eat peeled bananas, to help them remember meth, eth, prop, bute, 1, 2, 3, 4 carbons. So let's start off by drawing out the parent chain. The prefix hex tells me that there are 6 carbons, 1, 2, 3, 4, 5, 6, and that they're all connected by a single bond because of the suffix ane. Now, looking further, we see that there are 2 other components here that have a yl suffix, ethyl and dimethyl. These YL suffixes tell you that these components are branching off from the parent chain. But where do they start splitting off? Well, that's what these numbers represent. They are addresses for where we're going to start branching off from the main parent chain. Now for this example, I'm going to count from left to right, meaning that this is carbon number 1, followed by 2, 3, 4, 5, and carbon number 6. But keep in mind, you don't have to count left to right if you don't want to. You can also count from right to left, making this carbon number 1, followed by 2, 3, 4, 5, and carbon number 6. So choosing the counting direction doesn't really matter when you're drawing it out, so long as once you've chosen the direction, you must stick with that counting direction. You cannot flip back and forth, counting left to right for one branch and then counting right to left for a different branch. In any case, I'm going to count from left to right, since that is what we're most familiar with, and I'm going to put placeholders for where these branches start sprouting out from. So the first one is an ethyl branch, and it sprouts out from carbon number 4. So here's carbon number 4, and I'm just going to put a placeholder here. Next up, I have two other branches. Both are sprouting out from the carbon number 3. So instead of a 3, I'm going to put the 2 placeholders here. Now, if this numbering system had been a 2, 3 instead, then I would just move one of these placeholders over to carbon number 2, and that's where my carbon branches would have been located, on the number 2 carbon and the number 3 carbon. So 1, 2 carbon, and number 3 carbon. But in this example, both branches sprout out from the carbon number 3 and carbon number 3, so I need to move it back in position. Now, there's no other branches that I can see in this name, so I'm just going to erase these numbers. This is just rough work. You're not supposed to have them there, but I wrote them in just to help you visualize which carbon was which. Alright, so on the 4th carbon, I have an ethyl branch, and since the prefix eth means that there are 2 carbons present, I'm going to draw in 2 carbons over here, and that would be my ethyl branch. Now on the number 3 carbon, we have a methyl branch. Looking back at the chart, we see that the prefix meth means that there's 1 carbon in that branch, so each of these placeholders contain a single carbon. Now the reason why they put a di prefix here is to show the reader that there are 2 of these methyl branches. So instead of writing 3-methyl twice, it's a bit of a shortcut to say 3, 3 dimethyl. So 2 methyls, and they're both located on the number 3 carbon. Alright, so we've got the main parent chain, the trunk of our tree, hexane. We have 2 types of branches, the ethyl branch located on carbon number 4, the methyl branch located on number 3, and of course there's 2 of them, one sprouting up, one sprouting down. So all that's left to draw on our tree are the leaves, and that would be our hydrogen atoms. Now let me just erase these boxes. And there you have it, 4-ethyl 3,3-dimethyl-hexane drawn in a condensed structural diagram. If I were to draw it in a line diagram, it would look like this. 1, 2, 3, 4, 5, 6 for the main parent chain, 2 carbons for the ethyl branch, 1 carbon for the methyl branch here, and 1 carbon for the methyl branch there. And as was mentioned in our previous video, it doesn't matter if you draw the ethyl group as popping up, or popping down, pointing to the right, or pointing to the left. It really doesn't matter. Since the single bonds are connected by sigma bonds, they are allowed to freely rotate. My only requirement is that the vertices must be obvious and that you try not to make it too crowded so it's easy to read. Alright, so what I want you to do is try out these 2 sample questions. Based on the name, I want you to draw the structure. So press pause. When you're ready, press play, and we will take it up. Okay, in the first example, we look all the way at the very end, and we see that the parent chain is decane. The prefix dec means that there are 10 carbon atoms in the parent chain, and the ane suffix tells me that they're all connected by single bonds. So there we go, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 carbons. Now I'm going to put in placeholders for where the branches start coming out from the parent chain. The first is a 5 for the butyl branch. I'm going to count from left to right, so 1, 2, 3, 4, and 5. There's my placeholder. The next is 4, 5, and 6. So 1, 2, 3, 4, 5, and 6. We then have more branches popping out from 2, 4, 6, and 7. So carbon number 1, carbon number 2, 3, 4, 5, 6, and 7. And then one more branch popping up from carbon number 7 as well. So 1, 2, 3, 4, 5, 6, and 7. So another branch right here. Looking back at our chart, butyl with the prefix but means that there are 4 carbons in this branch. So I'm going to draw 4 carbons here. 1, 2, 3, and 4. Again, I don't care if you draw them to the right, to the left, or even if you did this, so long as I can see that there are obviously 4 vertices, 4 carbons. That's really all that matters to me. So there's our butyl branch. Let's take a look at the next one. It says triethyl. The prefix eth means that there are 2 carbons in this type of branch. So each of these requires 2 carbons. So on the 4, 5, 6, we got carbon number 1 and carbon number 2, carbon number 1 and carbon number 2, carbon number 1 and carbon number 2. So each of these 3 ethyl branches have 2 carbons. Again, instead of saying 4-ethyl, 5-ethyl, 6-ethyl, we use the tri prefix to tell the reader as a shortcut that there are 3 of these ethyl branches located on the 4th, 5th, and 6th carbon. Same goes for the methyl branch, where the meth prefix means that there's only 1 carbon in each of these branches. So 1 carbon here, 1 carbon here, 1 carbon here, and 1 carbon here. Once again, instead of saying 2-methyl, 4-methyl, 6-methyl, 7-methyl, we save a little time by saying tetra as our prefix to say that there are 4 of these methyl branches and what are their locations. Our last branch is a propyl, and the prefix says that there are 3 carbons in this branch. So 1, 2, 3. Propyl branch. And there you have it. 5-butyl with 4 carbons. 4, 5, 6 triethyl, so 3 of these ethyl branches. 2, 4, 6, 7 tetramethyl, so 4 of these methyl branches, and 1 of these propyl branches located here. And then decane in our parent chain has 10 carbon atoms, all linked together with single bonds. Okay, 5,5-dibutyl 3,7-diethyl 2,2,6,6 tetramethyl nonane should look something like this. 9 carbons in the parent chain, 1, 2, 3, 4, 5, 6, 7, 8, 9. Dibutyl tells me that there are 2 of these butyl branches, which means there's supposed to be 4 carbons in them. And they're both located at the number 5 carbon. So 1, 2, 3, 4, 5. There's a butyl branch there with 4 carbons, and a butyl branch over here with 4 carbons. 3,7-diethyl with the prefix di telling me that there are 2 of these ethyl branches located on the number 3 and number 7 carbon. 1, 2, 3, 4, 5, 6, 7. And ethyl branches should contain 2 carbons each. 2 carbons each. 2,2,6,6 tetramethyl tells me I have 4, so that's a tetra, of these methyl branches, and they're located on number 2 and 2 carbon. So there's number 2 carbon, so there's 2 of them there. And also the number 6 carbon, and here's the number 6 carbon, again 2 of them here. And that's it. 5,5-dibutyl 3,7-diethyl 2,2,6,6 tetramethyl nonane should look like this. So now that we know how to draw a structure from the name, how do we do the opposite? How do we name a structure from the drawing itself? Well, we start with the exact same area, the parent chain. To choose the parent chain, you must find the longest continuous carbon chain. So no backtracking. Looking at this example, we see that the longest continuous carbon chain you can find is 8 carbons long. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. You get the idea. No matter what pattern you take or which path you take, 8 is the longest continuous carbon chain you can find. The problem with this particular example is that there are 3 different ways to choose a parent chain that has 8 carbons in it. But let's look at the first one for now. If this is the parent chain, then these 2 are propyl branches. The prefix prop means that there are 3 carbons in this branch, and here we see 1, 2, and 3, 1, 2, and 3. Meanwhile, these 2 are methyl branches, where the prefix meth means 1 carbon in this branch. 1 carbon, 1 carbon. So if we choose this to be our parent chain, the propyl branch and the propyl branch, the methyl branch and the methyl branch are pretty easy to identify and name. But let's take a look at our next example. If we choose this to be our parent chain instead, again we see a propyl branch coming off from the parent chain, but then we see this odd branch, which becomes a little bit of a problem. It branches off the parent chain once, but then branches off again in 3 separate directions. This makes it a little difficult to name because now there are 1, 2, 3, 4 carbons, which should be a butyl, but how does the reader know you're talking about this butyl with 4 carbons and not this butyl with 4 carbons or this butyl with 4 carbons? So naming a branch that branches off a second time is a little more complicated. The same thing happens with this example, where if you chose this as your parent chain, again you've got a propyl branch popping up, no problem, easy to name, but then you run into that problem of a branch that branches off again. So in a situation like this, where all 3 of them give you the longest possible continuous carbon chain of 8, and you need a tiebreaker, choose the one where it's easy and straightforward to name the branches that pop out from the parent chain. Alright, so let's focus on this one now. First up, let's name the parent chain. Because there are 8 carbons all connected by single bonds, the parent chain is called octane. Oct for 8, ane for single bonds only. Now, instead of saying propyl-propyl, we can do a little shortcut and use the prefix di to represent 2 of these propyl. The same goes for the 2 methyl branches. Instead of saying methyl-methyl, just say dimethyl. Now we need to tell the reader where these branches sprout out from. So what are their address numbers? Now earlier when you were drawing the structures, it didn't really matter if you were counting left to right or right to left with regards to the address numbers. But now that you're creating the instructions for the reader, it does matter if you choose left to right or right to left. Let's take a look at it. Going left to right, we see the address numbers for our branches are 2 and a 2 and a 4 and a 4. But if we choose to count right to left, we see the address numbers are now 5 and 5 for my propyl groups, and then 7 and 7 for my methyl groups. So when choosing the counting direction for our parent chain, we always choose the one with the lowest address numbers. Imagine if you had an alkane that went like this, and then methyl. Would you want to have your reader count to 23 methyl, or just say 2 methyl instead? Obviously this method over here is less likely to incur errors. So we prefer the counting method with the lowest address numbers and not the higher ones. So for this example, we will count from left to right, giving my methyl groups a 2 and a 2 address number and a 4 and a 4 address number for my propyl groups. Alright, so let's put it all together. When assembling your tree, we always go in alphabetical order. So in this case, M comes before P. So I'm going to write down 2,2-dimethyl. You will notice that we use a comma to separate numbers from numbers, and we use the hyphen or the dash to separate numbers from letters. We then place in our propyl groups, so dash to or hyphen to separate numbers from letters. 4, comma 4, again the comma is used to separate numbers from numbers, then another hyphen between numbers and letters, dipropyl, and since there are no more branches left, time to put in our parent chain, octane. You'll notice that there's no gap or space between letters. So once again, when assembling the parts of our tree, we must first go in alphabetical order. M comes before the P, so 2,2-dimethyl. Make sure you put the comma to separate numbers from numbers, hyphens to separate numbers from letters, followed by the propyl branches. So again, hyphen to separate letters from numbers, comma to separate numbers from numbers, and another hyphen to separate the number from letters. So dash 4, 4 dash dipropyl. Then finally, since there's no more branches left, just our parent chain, octane goes at the end. No gap, no space between letters and letters. Now be careful when going in alphabetical order. We ignore the prefixes and go straight to the first letter of the branch name itself. In this case, M comes before the P. Alright, so the name of this chemical compound is 2,2-dimethyl-4,4-dipropyl octane. Alright, so I want you to give these 3 a try. Name these 3 alkanes. Press pause, and when you're ready, press play, and we will take it up then. Okay, looking at the first example, 6 was probably the longest continuous carbon chain you could find, and you could do that by choosing this as your parent chain, or this one, or this one. It really doesn't matter which one you chose, they're all the same name in the end, which I'll explain in just a few moments. But for now, let's just choose this as our parent chain. Since there are 6 carbons all linked together by a single bond, the parent chain is called hexane. We see 2 ethyl branches coming out from the parent chain, but instead of saying ethyl-ethyl, we instead write diethyl. And over here we see a single methyl group coming out from the parent chain. Now be careful, some students think, oh, shouldn't this be propyl? Because there are 1, 2, 3 carbons. But keep in mind, this carbon is not part of the branch, this carbon is part of the parent chain. So you must not count it as part of the branch. So it is an ethyl branch with 2 carbons. Okay, so we've identified the branches, we've identified the main parent chain, there's nothing else to look for, so at this point we have to choose a counting direction to assign our address numbers to these branches. If you go left to right, the address numbers are 3, 3, and a 4 for my branches. But if you go right to left, the address numbers become 3, 4, 4. So which is preferred, 334 or 344? Well, the official rule for choosing the counting direction is called the rule of first difference. How it works is you look at the first column and choose the counting direction that gives you the lowest number. Now in this case, it's a tie. They're both 3 and a 3. Neither of them is lower than the other. In the event that you need a tiebreaker, you move to the next column. Here we have a 3 and a 4. Since 3 is lower than 4, we choose this left to right as our counting direction. Now, if this had also been a 3, you would go for another tiebreaker by moving to the next column, and so on and so forth, comparing to see which one's lower. This is why it's called the rule of first difference. The first column to find out where there is a difference is going to be the one that will decide for you which direction you're going to count in. Now, if both directions give you the same number, that just tells you it doesn't matter. Basically, it's a mirror image. So for example, here we have a methyl group popping out from the number 3 carbon, but it's the number 3 carbon whether you choose to go left or right, or if you choose to go right to left, it's still the number 3 carbon. So in this case, it doesn't matter if you go left to right or right to left. In any case, with this example, 3 is definitely lower than 4, so we are going to choose this counting direction, left to right. So my address numbers are 3 and a 3 for the ethyl groups and a 4 for the methyl group. Alright, let's put it all together. Alphabetically, the ethyl branches should go first. Again, we ignore the prefix when we're looking at alphabetical order, and instead we compare the first letter of the branch name itself. So we have 3, 3, comma to separate numbers from numbers, hyphens to separate numbers from letters, diethyl. Next we're going to put in the branch for methyl. Again, hyphens separates letters from numbers. And then we put in our parent chain with no gap or space between letters and letters. So this one is 3, 3 diethyl 4 methyl hexane. Now, as I mentioned earlier, it doesn't matter if you chose this as your parent chain, because these two are ethyl branches coming out from the number 3 carbon. But if I had chosen this as my parent chain, you still have 2 ethyl branches still coming out from the number 3 carbon. And if I had chosen this as my parent chain, I still, again, have 2 of these ethyl branches popping up from the number 3 carbon. So it really didn't matter which one I chose. Alrighty, let's move on to the next one. So the parent chain is nonane with 9 carbons all linked together by single bonds. And we have 3 of these ethyl branches, which we will shorten to triethyl. If I count left to right, my address numbers are 5, 5, and 6. But if I count right to left, my address numbers are 4, 5, 5. Looking at the first column, I see that the right to left has a lower number with the number 4. So I'll choose right to left as my counting direction, giving my ethyl branches an address number 4, 5, and 5. And putting it all together, we get 4, 5, 5 triethyl nonane for this chemical compound. Moving on to the last one, I've chosen octane to be my parent chain. Once again, you could have chosen this one as well, but as you'll see in a bit, it's going to be the exact same thing. Whether or not you chose this as your parent chain, this as your parent chain, or this. In any case, we have 2 propyl branches, which we're going to simplify to dipropyl, and 1 methyl branch. Choosing to count from left to right gives you address numbers of 4, 4, and 5. while going right to left gives you address numbers of 4, 5, 5. Since the second column is the one with the first difference, and 4 being the lower number, we choose left to right as our counting direction, resulting in the address numbers of 4-propyl, and 5-methyl. Putting it all together, M comes before P, so it's 5-methyl, 4,4-dipropyl octane, with hyphens separating numbers from letters, commas separating numbers from numbers, and no gaps between letters and letters. So, many of the rules that we learned for naming alkanes can be applied to naming alkenes and alkynes as well. But there are some differences, so let's take a look at this example here. What we're going to do is we're going to chunk into smaller pieces and try to find meaning from it. Once again, we need to find the longest possible continuous carbon chain. In this case, there are 9 carbons, which is why we have a prefix of nona to denote this. Next up, you'll notice that there's an ethyl branch, 1, 2 carbons over here sprouting up from the parent chain, and there are 2 methyl branches coming out from the parent chain as well. So really, 75% of this name you already understand if you understood how to do alkanes anyway. It's just this one little part over here that's kind of confusing. Now, hopefully you can guess that the en comes from the suffix ine from alkenes, and that's to indicate the presence of double bonds. And since there are 2 double bonds, here and here, that's why we have the prefix di to say that there are 2 of these double bonds present inside our parent chain. And the same thing goes for the ine for alkynes to show that there's the presence of a triple bond here in our parent chain as well. So this naming system is very systematic. There's the red for our ethyl branch, green for our methyl branches, 2 of them, so it's dimethyl, nona for the parent chain with 9 carbons, and then diene to show that there's 2 of these double bonds, 1 and 2, and that there's a triple bond over here, ine. Now, what's interesting is the counting direction they've chosen. If you recall, the parent chain is the most important part of the organic molecule itself. Alright, so the branches are not as important as the parent chain. Since the double bond and the triple bonds are located within the parent chain, it is their address numbers that get priority, not the branch address numbers, but the double bond and triple bond address numbers. Must be the lowest possible values. So if I count left to right, the address numbers for my double bond it's located on the number 1 carbon. It's located on the number 2 carbon, and the triple bond is located on the number 4 carbon. Now, some students may ask, well, why can't you label this double bond as number 2 instead? And then you'd label this one as number 3. And then triple bond would be number 5. Well, notice how this is a much lower number than this one. So right off the bat, I know I can't use this numbering system. I have to use 1, 2, 4 instead. All right. Now, what happens if I count right to left? Well, I think it's obvious. By counting right to left, your multiple bonds get a much higher value. So even though the branches would get a lower value, that's great, but the branches are not as important as the parent chain. So we can't count right to left. The address numbers of our multiple bonds are too high. We have to count left to right instead. So hopefully the address numbers now make sense. 7-ethyl, 7-ethyl, 6,6-dimethyl, 6,6-dimethyl, nona, 9 carbons in my parent chain. And within the parent chain, I have 2 double bonds, diene, and they're located on the number 1 and number 2. Number 1 double bond, number 2 double bond. And then, of course, number 4 carbon has my triple bond located there. Now, some common questions I get from students. Why do you list the double bonds first and then the triple bond? Alphabetical order. E comes before the Y. Alright, so the di, the prefix di does not count for alphabetical order. The E does and the Y does. Now another question students ask, they understand where the Y and E came from, alkyne, but what happened to the ene over here? There's missing this one letter E. It's been removed from the end. I like to think of the letter E as a period to end the sentence. Alright, so the E is only placed at the very end of the whole name itself. Since there's more after the ene, we can't put an E to end the statement here. The E must be placed at the very end to end the statement. Alright, so the naming system for alkenes is very, very similar to alkanes. And as you can see, it's very systematic. And this is a very important skill set to have to be able to chunk or break apart the answer and try to compare it to the structural diagram to try to find meaning, try to understand why it was named in this manner. Because I can't teach you every single permutation, every single naming convention, there will be some situations where you will have to try to find meaning and try to make up your own rules based on the answer and comparing it to the structural diagram and try to understand why they named it that way. All right, let's keep going. One other thing we need to keep in mind when it comes to naming alkenes is that the main parent chain must contain the multiple bonds inside of them. The multiple bonds, the doubles and the triples, must get priority. And because they are important, they must be part of the parent chain. So your parent chain, when it comes to alkenes and alkynes, must include the multiple bond. Even if you have a situation where you can find a longer carbon chain. So in this example over here, we have 5 carbons. Unfortunately, the double bond is not included within the parent chain itself. As such, this parent chain is not allowed. But if you select this as your parent chain, we now see that the double bond is within the parent chain itself. Even though there's only 4 carbons within it, while this one has 5, this is the only valid one because it contains the double bond, while this one does not contain the double bond. Alright, so if we look at the name for this structure, let's take a look at this. Here we have 1, 2, 3, 4. That's why it's bute. Because there's a double bond within the parent chain, we have an E, and of course there's that letter E at the very end because there's no triple bond. That ends the statement. There is also an ethyl branch present. And once again, we must choose a counting direction that gives the lowest number to the double bond. In this case, 1 is the lowest possible number. If I'd counted the other way around, the double bond would have been given a number of 3, an address number of 3 instead. But 1 is better than 3, so we can't count right to left. We must count left to right instead. Alright, so therefore we have a 1-ene to show the location of the double bond, bute because there's 4 carbons in our parent chain, and on the number 2 carbon there's an ethyl branch. So 2-ethyl-bute 1-ene. Now, be careful, your textbook is kind of simplistic, and it prefers to write this name out in this manner instead, where it'll say 2-ethyl-1-butene, where the 1 tells you the location of the double bond. This is my preferred method because it's a lot more versatile. This method allows you to mix and match, so if you had double bonds and triple bonds present, it tells you exactly the 1, 2 is for the double bond, the 4 is for the triple bond. But with this method down here, it places all the address numbers in front of the parent chain, but then what if I had a triple bond and a double bond? How do I know what number belongs to the double bond, which number belongs to the triple bond? I gotta put a number here. Let's pretend it's a 1 and a 3. Okay? It doesn't allow you to differentiate which one's a double bond, which one's a triple bond. So this method is very, very simple. It only works when there's just one double bond or just one triple bond, and that number tells you the location of where that multiple bond is. Whereas this method up here allows you to differentiate the address numbers of the double bonds and the triple bonds in the same molecule itself. Alright, so the examples in your textbook will be very, very simplistic. It'll only contain one double bond or one triple bond, and that is the location for it. Alright, so let's take a moment to try these examples out. Press pause. When you're ready, press play, and we will take them up. Alright, so for A, you should have chosen this as the longest continuous carbon chain that you could find that includes your double bond. Because there are 7 carbons in the parent chain, we're going to use the prefix hept, and then we're going to use the suffix "-ene" to show that there's a double bond present. Now the question is, do we count left to right in blue, or do we count right to left in red? Now remember, the branch numbers are not as important as the multiple bond address number. It should get the lowest possible value. So if you choose left to right, the multiple bond gets an address number of 2, but if you chose to go right to left, you get an address number of 5 for the multiple bond. Obviously 2 is better than 5, so we're going to count from left to right and give the double bond an address number of 2. So that would be a hept 2-ene is our parent chain. Looking around, we see the following branches. 2 ethyl branches, one located at the 3, the other located at the 4, so we say diethyl, and a methyl branch located at the number 2 carbon. When we put it together alphabetically, ethyl goes first, followed by the 2-methyl, and then hept 2-ene. Again, no gap, no space between letters and letters. Commas separate numbers from numbers, and then the hyphen separates numbers from letters. So this one would be called 3,4-diethyl 2-methyl hept 2-ene. In example B, you should have chosen this as your longest continuous carbon chain that includes all your multiple bonds. Since there are 8 carbons, we use the prefix octa. And since there are 4 double bonds, 1, 2, 3, and 4, we say tetraene. where tetra means that there are 4, ene meaning double bonds, so 4 double bonds. And where are they located? At the 2, 3, 5, and 6. So whether you counted left to right in red, the double bond location is the 2, 3, 5, and 6. Or if you chose to go right to left in blue, the address numbers of the double bonds are still 2, 3, 5, and 6. So in both directions it's 2, 3, 5, 6. So I'm just going to write 2, 3, 5, 6 regardless of which direction I chose. Now one other thing to keep in mind, sometimes you'll hear it or see it being written as tetraene, but I've also seen it written as tetrene. It has been my experience that when you see two vowels side by side between the prefix and the name itself, we typically remove the vowel from the prefix. And so instead of tetraene, we just write tetrene. Same thing happens over here. If there are two vowels side by side, you would take away the A from the prefix here. So typically it's the A prefix, penta, hexa, hepta, octa, nona, deca. That A gets removed, and you're left with just the basic prefix. But in this example, since there's no two vowels side by side, it's an A, which is a vowel, and T is a consonant, you can keep the A in there. So octa, 2, 3, 5, 6. And in this case, I'd probably prefer tetrene rather than the tetraene. So get rid of that A because there's two vowels stuck side by side. All right, and that would be our parent chain. Now let's take a look at our branches. Here we have an ethyl branch, and here we have a methyl branch. Because the counting direction for the double bonds is the same going both ways, red and blue, you get 2, 3, 5, 6, we need some sort of a tiebreaker. So the next tiebreaker we should use is to give the lowest possible number for the branches. If I count from blue, my lowest possible number for the branches are 4 and 5. And if I count with red, my address numbers for the branches are again 4 and 5. So that doesn't help us in terms of making a tiebreaker because they're both identical. So the next best thing is to use the alphabetical order as the tiebreaker. Since E comes before M, ethyl should get the lower number. If ethyl should get the lower number, we got to use the blue counting system instead of the red counting system. That way ethyl gets a 4 instead of a 5 address number. Alright, so it's very systematic. Once again, let's go over the priority list. Priority list is to give the lowest numbers to the multiple bonds, but as we saw, going left to right, it's identical in both cases, 2, 3, 5, 6. Okay, fine. The next tiebreaker is to give the lowest number to the branches. But again, with the branches, we still get a 4 and a 5 in both directions for the address number of our branches. So the final tiebreaker, alphabetical order. Give the ethyl the lowest possible number because alphabetically it comes before methyl. Ethyl comes before methyl. All right, let's put it all together. And we get 4 ethyl, 5 methyl, octa, 2, 3, 5, 6 tetrene. In example C, you should have chosen 8 to be the longest continuous carbon chain you could find that includes your multiple bonds. So we'd write octa, ene, and ine to show that there's a double bond present and a triple bond present. But now we got to pick and see which direction we should choose. Should we choose left to right in blue, or should we choose right to left in red? Again, the multiple bonds get priority over the branches, so we got to make sure they get the lowest number. If we choose red, the address numbers are 2 and 7, but if we choose the blue counting system, gives us address numbers of 1 and 6 for the location of the multiple bonds. Obviously 1 and 6 is better than 2 and 7, so we will choose the blue counting system, giving the triple bond a location of 1, and the double bond gets a location of 6. Now again, I see two vowels side by side. The A and the E are right next to each other, so when two vowels are side by side, remove the vowel from the prefix. So instead of octa, we say oct, 6n, 1 ine. But that being said, I don't mind if you keep the A off or if you keep the A on. It's a very, very minor thing. It's just some students ask why do they see it in the textbook with the A sometimes and why do they see it without the A sometimes. It's like I said, I think based on what I've seen anyway, if you see the A and the E, two vowels side by side, typically remove the A from the prefix itself. All right, so keep it on, keep it off. Doesn't make a big difference. I won't deduct marks for this. It's very, very minor. All right, so that's our parent chain and the proper counting direction. Now let's identify the branches. 6 and 7 dimethyl, and then the 4 and the 5 diethyl. Putting them all together alphabetically, ethyl comes before methyl, so 4, 5 diethyl, 6, 7 dimethyl, oct, 6 ene, 1 ine. Once again, the E on the ene is only placed at the very end of the sentence, of the end of the name itself. Now, this example D is pretty straightforward in the sense that there are no branches. There are 5 carbons located here, 1, 2, 3, 4, 5, hence the penta suffix. And then we have 1 double bond, so ene, and 1 triple bond, ine. With the blue numbering system going from left to right, the location of the multiple bonds are 1 and a 4, while the red counting direction going from right to left also provides us with a 1 and a 4 for the location of the multiple bonds. As such, we need a tiebreaker. Quite often, students will mistakenly think that the triple bond is more important than the double bond. That's not true. We're just going to go in alphabetical order in order to break this tiebreaker. Since ene is alphabetically superior to ine, the double bond should get the lowest possible number, and thus we're going to use the blue counting system to give the double bond priority. So we have penta 1 ene for ine. Again, when I see the 2 vowels side by side, I'm going to remove the vowel from the penta and leave it as pent 1 ene for ine. Now, please keep in mind the double bond only got priority because we needed a tiebreaker. It's not always superior to the triple bond. If we look back to the previous example, we gave the triple bond the higher number and the double bond the lower number because going this direction gave us the lowest possible number for all the multiple bonds. While with example D, going in both directions gave you the exact same number, so we needed a tiebreaker, and alphabetical order was the tiebreaker in this case. Hopefully by now you're starting to get the hang of this. So 7 carbons should be the longest continuous carbon chain you can find that contains all the multiple bonds within your parent chain, hence the reason why it's called hepta. And then the location of the double bonds is going to be a 2 and a 5, going in both directions, so it really doesn't matter which direction you chose. And because there's 2 of these triple bonds, we say di as a prefix, ine to say that there's 2 of these triple bonds. And on the 4th carbon, we have a propyl branch. Since there's a vowel and a consonant, so there's no 2 vowels side by side, we're allowed to keep the a on the prefix itself. Putting it all together, we get 4-propyl hepta-2,5-diine. Alright, so the last thing we need to worry about when it comes to alkenes is geometric isomerism. So geometric isomerism, also known as stereoisomerism, is where the molecules have the same molecular formula and their atoms are bonded together in the same sequence, but their orientation in 3-dimensional space differs. Let's take a look at these 2 examples. Because this is an alkane, you're always connected with CC single bonds. And if you recall, single bonds are comprised of sigma bonds, which is a head-to-head bonding of the electron orbitals, and that allows you to have them rotate freely along the horizontal axis, which means pointing up or pointing down makes no difference. It's the same thing. Both exist at the same time, since this bond is free to rotate. But with a double bond, we have both a sigma and a pi bond present between these 2 carbons. As we said, the sigma bond is a head-to-head overlap of the electron clouds, which allows for free rotation along the horizontal axis. But with a pi bond, we have a side-to-side overlap between these 2 p orbitals. This keeps them linked together and prevents them from rotating along the horizontal axis. So as we see in this animation, as we try to bend it, it doesn't allow it to work because then this p orbital over here, or rather the lobe of this p orbital, if it tries to rotate this direction, it'll drag along this p orbital with it, or this lobe rather, and it'll rotate along both of them. So they are not free to rotate about each other independently. They are connected. So going back to this example, whether it's pointing up or pointing down, they're both called butane, because they're allowed to rotate freely along the horizontal axis, so both up and down is allowed. However, the moment I put a double bond in between these 2 carbons, they are now locked in position. I cannot rotate the H down here and the CH3 up here to make this version because the double bond prevents you from rotating freely. So while this version of butane and this version of butane are the same, the moment I put a double bond in and call it but2ene, they are no longer the same structure. This version of but2ene will react differently than this version of but2ene. They will both have different physical and chemical properties because of their different structures. So if these two structures are different, then I need a way to tell the reader how to differentiate between this butene, where it's locked in the position pointing up and pointing down, or this version of butene, where it's locked in position pointing up and pointing up. Which is the reason why we have the prefix trans and the prefix cis, where trans means to cross or opposite sides, and cis means same side. So looking at this example, you would first highlight the main parent chain, and then what I like to do is I like to draw a border where the double bond is present. Then I look to see, has the parent chain crossed over from one side of the border to the other side of the border? In this case, yes it has. The parent chain started off on this side of the border and ended up on that side of the border. So you could say it has been transported to the opposite side. Whereas if you look at this example, again, we highlight the main parent chain, then I draw a border along the double bond. You'll notice that the parent chain does not cross over the border, it stays on one side only. It never makes it to the other side of the border. So we call this cis, meaning the same side. Alright, so all you have to do is just draw the parent chain, draw a border line that follows the direction of the double bond. So the double bond crosses like this. I'm going to extend the double bond, if you will, and make a border out of it. The double bond goes in this direction, so I'm going to extend it and make a border out of it. The parent chain crossed this border, crossed the border line, so it's been transported to the other side. This one does not ever cross the border, so here's the border. The parent chain never appears on this side, the parent chain only appears on this side, so we say cis instead. Now, just be aware, ChemSketch does not use the cis-trans method. Instead, it uses the EZ method. So while we would call this one cis-butene, because the parent chain appears on one side of the border, so if this double bond was the border line, the parent chain only stays on one side. ChemSketch will instead call it Z-butene, where Z is German for zusammen, which means same side. All right. Versus if I lifted this one up and made it opposite side, so here's the border, now the parent chain crosses to the other side, you'll notice that ChemSketch now calls it E-butene, which is German for entgegen. Entgegen means opposites, right? So entgegen, opposite side or trans, and then if I bring it down over here, then it'd be called cis or zusammen butene. Now just be aware the E method and the Z method, that's not in our curriculum, so I'm not going to test it, nor can I accept it as an answer. On the test it must be either cis or trans. I'm just showing you the EZ method. It is a little more versatile in that it allows you to do multiple bonds present. So for instance, if I did this, where one of the double bonds is in the cis conformation, so same side, and the other one is in the trans conformation, so opposite side. Well, if I generate the name, we see it says 2Z, so the number 2, 1, 2. The double bond number 2 is using the Z conformation. Z stands for cis. And the number 4 double bond, so 1, 2, 3, 4th carbon double bond, is in the entgegen or E, trans conformation. Okay, so this method allows you to have multiple double bonds, and each of these double bonds could be positioned in a different way. And the EZ method allows you to determine the number carbon number 2, that double bond is in the Z, while carbon number 4, this double bond is in the E conformation. So once again, ChemSketch uses Z to mean cis and E to mean trans. So how I remember this is Z stands for zusammen side. Sort of. That's a stupid way of memorizing it, but whatever. It works. All right, so if the parent chain is on the same side, we say it's Z. And then E is the other one when it's opposites. But for the purpose of our course, we will only be using cis-trans. We will not be using the EZ method. As such, there will only be ever one double bond that will require you to label as cis or trans. I will not have multiple double bonds, each with a different conformation. Okay, so for our course, only one double bond, and it'll either be cis or it'll be trans, and so you will not need to use the EZ method. Now, be careful. There will be some situations where you might think that there is a cis-trans isomerism, but there actually is not. So take, for example, this one over here. I need to draw the parent chain and see if it crosses the border. All right, so if I draw the parent chain, I could have drawn the parent chain like this, Or I could have drawn the parent chain like this. Both are acceptable. Now, if I take a look at the border line, so I'm going to extend the double bond and turn it into a border. So border, 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 border. If I had chosen this as my parent chain, then it would have been trans. But if I had chosen this as my parent chain, then it would have been cis because it doesn't cross the borderline. So since both are legitimate, then that means there is no cis-trans isomerism in this case. All right. So if you can choose both of them, it doesn't make a difference. The reason why is because if I'd flip the CH3 down here and flip this CH3 down here, it makes no difference. It doesn't really change the structure at all. All right. So flipping these two made a difference because at the top it would have been a methyl plus a hydrogen. But then if I flipped it down here, it'd be a methyl and a methyl. So totally different substance, totally different structure. Whereas over here, if I'd flipped these two, the methyl with the methyl switch places, well, there is no difference. All right, you'd have a methyl-methyl at the top, hydrogen-methyl at the bottom. Over here, methyl-methyl at the top, hydrogen-methyl at the bottom, regardless of whether you flipped it. While flipping it here did make a difference. So looking at this example, I'm going to take the double bond, and I'm going to draw the border line. When I choose the parent chain, I could choose this as my parent chain, in which case, yes, it crosses to the other side. But I also could have chosen this as my parent chain, and you'll notice that no, it does not cross to the other side. It all remains on one side of the border. So because I could have chosen either or, that tells me that there is no cis-trans isomerism. More importantly, this group and this group are identical. So switching their places, made no difference. Thus, this compound over here has no cis-trans geometric isomerism. All right, so be careful with that. Typically on a test, I will give either an example of a cis or a trans, as well as one example where there is no cis-trans, just to make sure that you understand the difference and whether or not the cis-trans isomerism is present. All right, now the final type of stereoisomer is the enantiomer. Just like a pair of hands, they are mirror images of each other. So although they look the same, you can't actually overlap them. Since you can't actually overlap them, you need to have a way to differentiate between this version, enantiomer, and this version of the enantiomer. And so they use the letters L and D to differentiate between the two. But again, this is not in our curriculum. I just wanted to introduce this one to you. As I said before, there are many, many, many types of isomers, of which there are only two major ones that we have to worry about. The first being a structural isomer, where it's a totally different structure, and the second being a geometric isomer, where you have to worry about whether it's oriented up or up-down, which direction is it locked in position. Now, when it comes to alkynes and their triple bonds, due to the flat or linear nature of the triple bond, there is no cis-trans geometric isomerism for this one. All right, there's no pointing up or pointing down. The triple bond kind of forces everything to be in a nice, rigid, linear, or flat shape. With a flat shape, there is no up-down. So, geometric isomerism only exists for alkenes, all right, because they're locked in position once they've rotated. It does not exist for alkanes because they're not locked in position. They're allowed to rotate freely, so it doesn't matter if pointed up, pointed down, they both exist. And then it doesn't matter for alkynes because there is no up-down. They are perfectly straight and linear. All right, and that is how you name simple alkanes, alkenes, and alkynes.